Validating a binary search tree. Given the root of a binary tree, determine if it is a valid binary search tree. And a binary search tree is defined as it's a tree, it's a binary tree, so meaning each node has at most 2 children, and it has a property where everything going down to the left is smaller than the thing above it, and everything going down to the right is going to be larger. So this page has a couple of examples. If 2 is your root, and 1 is the left and 3 is the right, this is a valid binary search tree because 1 is smaller and 3 is smaller. However, in this example, if you have 5 as a root, 1 going down to the left, okay, that's smaller, great, great. But then going down to the right, 4 is also smaller, so therefore it's going to be not a valid binary search tree. Another thing to note too is that, okay, suppose 1 is, 1 to the left, 5, and then 4 going down to the right. If this was, say, 8, that would be larger than 5, so that would not violate the binary search tree property. However, you have this child down here, 3. So regardless of what this first level child is, this 3 is smaller than 5, but it is reached by going down to the right from 5. Therefore, that would also make it not a valid binary search tree. Does that make sense? All right, so everything to the left is smaller, everything to the right, including children, has to be larger than the things above it. That's a binary search tree. So let's go into the actual problem. I'm not going to do it on LeetCode. I'm going to do it manually using C++, including all the test cases. So just to start up with boilerplate setup, the things that I've done ahead of time. This is a CMake file. It's very, very bare bones. This is about the minimum that you can expect to do and still be able to have like a single C++ file executable. Set the CMake version, name it to the standard. This sets the compiler flags if you get stuck in debugging, but it's not required. Name the executable, and then for some things, this actually adding OpenMP is not required for this particular problem, but sometimes I like to use it. It's very useful. This is mainly for like if you're testing like multi-threaded applications, like synchronization primitives. It's a nice way to quickly spawn a thread pool, but that is actually not important for this problem. But it's in my template that I use over and over again. And then in our main file, the C++ executable, I've got the main function, it returns 0, and then IOString import for, we're going to do print statements, obviously. And that's it. That's all we have. So in a binary search tree, the thing to note is that you have this global ordering. And when you have a global ordering, that lends itself to, okay, I'm no longer going to bury the lead. Probably the main approach that I like the best is to use a in order traversal with a counter to keep track of the global ordering. There's other ways you can do it. You can literally do like a recursive search with shrinking bounds on both the upper and lower parts. When you look at the asymptotic analysis, it all comes down to linear time and space. There's really not any way to do it in less than linear time and space. So I like the conceptually simplest approach of doing in order traversal. And we'll cover what that is as I type it out. So let's start off with defining some data structures. We are going to use, let's make a class node. And then the only difference between a class and a data structure in C++ is the default privacy. In classes, things are private by default. In structures, they're public by default. So I don't know. I like to use classes just to keep it all consistent. So it's going to have a few things. It's going to have an integer value for the sake of debugging. And it's going to have left and right children. And the way I'm going to do that is shared pointers. And that is going to require the memory header. Include memory. Shared pointer to a node, left, and right. Is that good? Is that good syntax? Oh, another thing we need, using namespace std. For the sake in production code, maybe you don't want to do this. You instead want to do something like that, where you have the standard prefix, but that adds a lot of characters in a very short window of interview time. So I'll do this up front and reduce that down a bit. But that said, while we're on the topic of namespaces, it is a good show of faith to add another namespace around it for the sake of encapsulation. So namespace, validate binary search tree. I'll just name it that, and then throw some brackets at the end. Okay, so this is a nice piece of encapsulation, I suppose. Let me take the main function out of it. Otherwise, it's not going to get found. Okay, so we have this node class with a couple of left and right children. And now let's make the actual function. So it's going to return a Boolean because we only care about if it's valid or not. Validated binary search tree. It's going to take a shared pointer as an input. Is that it? Is that all we need? Let's say, okay, the approach we want needs a global counter because we're going to do in-order traversal. I'll start typing out the in-order traversal and it'll make more sense as we go. Okay. So generally, when you have tree algorithms, there's going to be an element of recursion. Almost every kind is going to have recursion. And in recursion, you need a base case. So if root is null, then what? That's it. Just return true. It's fine. A node by itself with no children is going to be a valid binary search tree. For in-order traversal, you want to recurse left first. So for example, you're always going to go left if it's available. And then when one has no children, so you recurse left, there's nothing there. Then your base case back up, recurse right, there's nothing there. And then we go back up to 5. We've already traversed left from 5, so we're going to go down to 4. And before processing 4, we're going to go down to 3. And then, it's 2 children are null. We're going to process 3, back up to 4, process 4, and then process 6 because it has no children as well. So the effect is going 1, 5, 3, 4, 6. That's in-order traversal. And we want that property, that traversal, to have a globally monotonic non-decreasing order. Okay. The way we implement that is we recur select. So bool. This is actually a good time to talk about the global counter. So I'm going to add that as an input. Oops, that's going to ampersand goes there. Counter, root left, counter. And the reason I'm doing a counter as an argument instead of, say, like a global variable is mainly for the sake of code cleanliness encapsulation. Doesn't make a whole lot of difference in runtime, but it's easier to keep straight and easier to not make mistakes if you're in, say, like a multi-threaded environment. So, for example, another approach you could do is breadth first search based, or let me think about this. If you were to try and multi-thread this, you could do depth-wise partitioning of the tree in order to split them among multiple threads. And then you compare their results in it would be a logarithmic span. And then that would be one way you could multi-thread this out. And to do something like that, you need to have several different of those variables. So like a counter. And I'm getting quite scattered in this explanation, but all that is to say, if you see a clean way to not use a global variable and instead implement it some other way, such as through an argument input, do that. All right, so counter we recurse left. Now that that is done, we check the results because we can gain back some real world runtime if we break early. So if okay, so if the left subtree is not a valid binary search tree, we break out early, and that's fine. Now we need to actually visit the node that we're at. So if the value of the root is less than the counter, then we break out early. Now that we've passed this, we need to increment our counter up. And this simple assignment is safe to do because we already checked that the counter is not already greater than our value. So we would not be decreasing it by doing this. We'd only be setting it to the same value or higher. We visited the root, and then we need to visit the right. Root right, and the counter. And then we check it. And then if all of these checks pass, we can finally return true. Realistically, we could just return the output of this final recursion down to the right and it would have the same effect, but I think this is a little bit cleaner to read and understand what's going on. So we've got base case. Base case, I'll comment it. Recurse left. And then we visit the root. And then we recurse right. And you could just as easily go right first and then visit and then go left, and that would still be an in-order traversal, and then you'd have to deal with a decreasing counter instead, but same. There's no algorithmic difference there. So here's our main function. That's pretty much done. That's all there is to it. Now the tricky bit with doing it in yourself from scratch is getting it right as far as memory integrity. So for example, on the LeetCode site, you can see that it's doing just regular pointers. Now that's easier to implement, but it's technically bad practice. And if you can avoid it, you should. So for example, you could use shared pointers, which are from the memory header, which will automatically free the memory after there's no longer any references to that memory remaining. So like in its destructor, there's a shared counter, and then when that counter hits 0, it frees the memory. It'll do all that for you, and then you no longer have to like call your own delete loop. Now there's various reasons why you might still do it yourself anyway, but this is like a good backup guarantee where if you don't implement your delete function correctly, the memory still gets freed and you don't have a leak. But the syntax is a little different. So let's go ahead and create some test cases and you'll see how to deal with that. What I'm first going to do here is create a constructor. So node, give an integer value, and then val is going to take that value, and that's it. I think that's all I'm going to do for constructors. Yeah, that's fine. That's fine. Okay. Let's make some test cases. Void. I don't want to return a void. I want to return a shared pointer. I'm just typing this out. Okay, so we had that case of going, 1, 2, 3 are valid binary search tree. Very, very simple case. I'll do that just for the sake of sanity. So we have shared pointer node, and that's going to have a value of like 2. I guess. I'm going to give it a value of 1 and illustrate something. Let's see, instance matches argument. Something that can happen. Okay, for a bit of syntactic esotericness. When you're constructing a shared pointer, if you call the constructor this way, this is going to give you a null pointer. So shared pointers do support null, that is an option, and the way that you do that is through this, or null pointer, which is simply an alias for 0, or null. It's all the same thing. The compiler gets a 0 integer in this. If you want it to actually be a shared pointer, where the value of val is 0, you have to do something like this. Make shared, and then pass 0 to its constructor. And that's how you get an actual shared pointer with 0. Create an object that is owned by a shared pointer. Yeah, so that's it. And let's give it some left and right children. Left equals make shared node. And that's going to take, let's say, -1. And then on the right, we'll give it a value of 1. Now on LeetCode, you'll notice this array form of initialization where it goes, let's say 5, and then 1, 4, and then null, null for 1's children, and then 3, 6 for 4's children. This would be a breadth first search order. It depends how many test cases your interviewer wants you to do. If they want you to make a whole bunch, it might be worth investing the time to make a breadth first search based loop that will take an array and convert it into a binary tree that you can then analyze if it's a binary search tree or not. If you're gonna do just maybe 2 or 3 test cases, it's okay to hard code them. That is something that you should check with your interviewer ahead of time. I'm not gonna do that here. I'm just gonna do maybe 2 test cases and then call it good. So let's do another test case, case 2, and then let's give it some values. Let's say let's do similar to this. So 5, 1, 4, 3, 6. But I'm gonna make this an 8 to show that this is so 5, 1, and then 8, 3, 6, and that will show that it's still not a valid binary search tree. 5, 1, 8, 3, 6. All right, so 5. I'm gonna write that down so I don't forget. All right, so 5 on the root. And then we have 1 as its left child, 8 as its right child, and then for the right node, we're gonna give it a couple children, 3 and 6. Let's say root right left. That's going to be a value of 3. And then root right right. That's going to have a value of 6. And this one should be not a valid binary search tree. Simple valid case, invalid case. So we've got our 2 test cases, and we've got our main function, and we've got our data structure. Let's start making some of the code to actually call it. So I'm going to make a function called just run that will take a single test case and run it, and that way I'm not repeating myself as far as print statements go. So shared pointer to a node, call it root, and then what it's going to do is it's going to call validate binary search tree. It's going to get the result, and we're going to print it out. The result is just true or false. And it needs a counter. Okay, so here's another thing. Can we initialize it with a default? Actually, okay. Since this needs to be a global counter with a global ordering, what I'm gonna have to do is initialize it. Now in C++, the way that you initialize an integer is you have to just basically set it to like int min or something. Int 32 min. Is it supported? So this is an option. Must be non-const to an L value. Okay, so in that case, we can't do it there. What I'm going to do instead is make a wrapper function to kick it off. So it's going to return the same thing and take the same arguments almost, except it's not going to have that counter. Let's say, okay, integer counter equals 32 min, and that should kick it off just fine. So this expands to this. And this is built into the compiler, but another option that's probably a little more, maybe a little more compatible, a little more robust, perhaps, is to use, okay, there's a header called limits, and it gives you access to a function called numeric limits. So instead of using a macro, you could also do something like int counter equals numeric limits integer min. And this is probably a little easier to remember because it's numeric limits and then your data type and then min. Now notice that this also has syntax for like if you have if you're using a floating point number or a double, so something like double lim numeric limits double, get that spelling right. You can do infinity, and you can do minus or plus, and then that will always lose in a comparison of like greater than or less than. However, that is not supported for integer types. It'll just give you a value of 0, which is not what you want. You're going to use a straight up counter. So int32 min is a common macro, or numeric limits, and you can give it like a typed function. Let's see. We've got that set up. Remove this default value. And I think that should, okay, that fixes that. That covers it. We've got our main function, we've got our kickoff function, we've got our couple of test cases, and we've got a test runner that will run a single one. So now we need the function to run multiple test cases, which we'll call this a couple times. So let's say, just call it test, I guess. It takes no arguments because it's going to call all of them. We're going to do run case 1 and run case 2. And that's it. And let's call test from the main function. Since we did wrap it inside a namespace called validate binary search tree, go ahead and end that. There. Now we know the namespace is over. We're here, and then we have to call it from with the prefix in order to access it from outside there in our main function. And I think that's it. Let's go ahead and talk through the test case. Now that was a lot all at once for code. Let's go ahead and talk through the test case. So we should run it as implemented. So I'm going to go ahead and shrink this, bring it over here so we can visualize it. No, I don't want that in the way. There, that's better. Okay, 1, 2, 3, this is our test case. Let's kick it off. So we've got this, we construct it as, well, 0 minus 1, 1. Let's go ahead and make this, let's make this test case match. So 2 would be the root, and then 1 is the left child. 2, 1, 3, 2, 1, 3. Okay, so we create the case, we run it, pass it to our runner, to our one that takes a single argument, fill out a binary search tree. This sets a counter to numeric limits, integer minus whatever, the negative one, and then it calls the main function. The main function takes these. Let's check the base case. So we're at 2. 2 is not null, so we're not going to hit that. We're going to recurse left. So recurse left with the same counter value. So now we're looking at -1. Let's see data structure. Our counter value is minus. I'm going to say minus infinity. It's not actually that. It's an integer value. But for the sake of argument here, we'll just say it's minus infinity. All right, recurse left. So now we're at 1. We're going to recurse again down to its left children. That's null, right child's null. Both of those are going to hit this base case and return true. So now that we've got true from going down, from after recursing from 1, we got this value here left is true. So that means we're not going to enter this, and we're not going to exit. So now let's visit 1. 1 is indeed, it's greater than the counter. So that's fine. 1 is not less than the counter. We're not going to enter this. And we're going to instead set the counter to 1. Okay. So now we're going to recurse. Well, we recurse right from 1. We recursed left from 1 before. That was true. Recurse right from 1. That's null, so that's also going to be true. So in that case, we're going to, so we finished visiting 1, and then we recurse right from 1. Now we're going to return true back up to 2. So now after 2, we finished recursing left. Now we're going to visit 2. So we're going to compare 2 to our counter. 2 is not less than 1. Our counter value is 1. So we're not going to hit this, and we're going to set our counter to 2. Now we're going to recurse right from 2. And then, so we're at 3, where we're going to first, so 3 is not null, so we're not going to enter the base case. We're going to recurse left from 3, that is null, return true. Recurse right from 3, that is also null, we're going to return true. So now we're visiting 3. Wait, I misspoke. Recurse left from 3, that's going to return true. Now we're visiting 3. 3 is not less than 2, so we don't enter this. We set our counter to 3. Now we recurse right from 3. That is null, so we're going to quickly return true back up to 3. And then we're going to go back up to 2. But we've already visited 2, so we're coming back from this. And we've gotten true back from 3. So that's it. We return true out from 2, and that's it. Our solution is 2. Return true from here, return true from here, and then we print it out. Now let's look at this case. 5, 1, 4, well, 5, 1, 8. Let's consider the 8. I like the 8 better. Okay, kick it off. 5 is not null, so we recurse left. 1 is not null, so then we recurse left again. Null is the base case, return true, and now we visit 1. Our counter, which was minus infinity, we're going to now set to 1. Our counter is now 1. And now we're going to recurse right from 1. That's null, so we'll return true automatically and then go back up to 5. Now we can visit 5. So we visit 5. 5 is not less than 1, so we don't enter this exit condition, and we set our counter to 5. And now we recurse right. Now in this picture it's 4, but in my example, I'm going to go with 8. So we consider that it's 8. Keep that in mind. 8 is not null, so we don't use this. We don't hit the base case. And then its left child is there. So let's go ahead and recurse down to 3. 3 is. So we're recursing onto 3. We're going to recurse onto 3's null children. So null, we're going to hit the base case there. That's true. And then we visit 3. 3 is not. Oh, it is. 3 is less than 5. So we're going to hit this exit condition. 3 is less than 5. 3 less than 5. In that case, we're just gonna automatically return false. So now we're hitting our exit condition. We'll quickly return false back to 8. 8 had recursed left, so now we're here. We got 8 back to here, and then left is false. So that we're just gonna follow that exit condition back up the chain. 5 is gonna return from here. This right call. This is gonna get back false there, false, and we're gonna return false from 5, and our final output is false. And that's it. That's our solution. So I'm going to go ahead and run these and see how we did. So make CMake, compile, and then it's called run or main. What did I call it? Main. That matches our mental step through. This first example is true. Second example was false. Okay. So is there anything else to cover? The main thing is to keep in mind are the syntax for shared pointers, which are a really nice touch to use. They don't really take more time than regular pointers. They're much easier to reason about. It's just a little trickier syntax up front, but once you're comfortable, then it works. So you can set set shared pointers with make shared, and then the data type, and you pass values to the constructor of. So for node, we pass this value to the node constructor. If you were to do make shared, some root value, and you pass it, you can kind of pass it 6 to the constructor. Does that work? Actually, I'm not so sure that it does. If you want to set a null pointer, which I think is the default, then you call it this way. If you want to set an actual value where you pass values to the constructor and it's a proper pointer and it's got valid memory, this will allocate the memory with make shared. So that's the distinction to keep in mind. This will set a null pointer. Oops. This will set an actual pointer with values passed to the constructor. And that's it. That's the entire thing. So let's go ahead and write out the approach. The approach is in order traversal with a global counter. It's not really global, but so it's a monotonically non-decreasing counter. And that's the algorithmic approach. We passed it through the function arguments instead of as a global. In order to keep things compact, we use an additional namespace to isolate our stuff a little bit better as well. That's a nice feature. And then in order traversal is O of n time and space. And the reason it's O of n space is because suppose you have a very, very long input where it's going all the way down to to one way. So for example, in this one, suppose this node didn't exist and suppose this node didn't exist. Your entire tree would be on the function call stack, and that would give you linear space. So that's why it's linear space. And then linear time is In the worst case scenario, your tree is indeed a valid binary search tree and you have to traverse the whole thing. Well, in that case, that's linear time. You're covering the whole thing. Now, normally with graphs, you would break out the runtime into a function of nodes and edges, so the circles and the lines. So these are nodes, these are edges, nodes and edges. In a binary tree, or really any tree with the where the number of children per node is has a max value. So in this case, it's a maximum of 2 children per node. If it's some constant that never changes, then you consider your edges and nodes to be asymptotically equivalent. So then your runtime collapses to O of n time and space because the number of edges and nodes are, equal more or less within some constant multiple. And then that's it. We visit every node once and we use the function call stack, and that's the entire thing. And you can't really do better than linear time and space because, well, if you can think of an algorithm where you don't have to touch every single node, that would be awesome. Now, maybe if you had to use a tree that was known to be a valid binary search tree in order to solve something else, then you could traverse the tree without having to actually touch on every single node, and that would reduce your runtime to logarithmic for the tree axis. However, we are in fact making sure that the tree is a binary search tree or not, and yeah, there's no way to do that. You got to touch on every single one, so you end up with this linear time. Anyway, that's it. You folks have a beautiful evening.